In this video, we will discuss about buffer and the calculation of pH of a buffer solution. Buffer solution is a solution that resists the change in pH when a base or acid is added to it. So a buffer solution usually consists of a solution of a weak acid and its salt, or a weak base and its salt. And because of the presence of acid and base in the same solution, this will resist the change in pH when we add extra acid or base to that buffer solution. So let's see how is that going to work. So here we can see a combination of acetic acid and its conjugate base. So this is a weak acid and this is going to be the conjugate base of our weak acid, that is acetic acid. So conjugate base is stronger than the weak acid. And now when we add acid to it, what happens is this strong base will react with the acid and it will go back to acetic acid. And when we add base to it, acetic acid will get neutralized by the base and it will move forward. The equilibrium will rise to the right side. Another buffer system is ammonia and ammonium buffer system. So in this case, when we add a strong acid, the base ammonia will get that acid and it will neutralize. So if you add a strong base to it, the ammonium ion will react with the base, the extra base, the invader, and we will get ammonia plus water. So how much acid and base it can absorb without changing the pH? That is called the buffer capacity of the system. So in order to have a large buffer capacity, a solution should have large concentration of both buffer components. That means the weak acid or base and its conjugate acid or base. Now let us see how to calculate the pH of a buffer solution. We can calculate the pH of a buffer solution using Henderson-Hasselbalch equation. That is pH equal pKa plus log concentration of conjugate base divided by concentration of the acid. So in other words, pH equal pKa plus log concentration of A minus, that is the conjugate base, and divided by concentration of HA, that is the weak acid. And now another way of calculation of the pH of a buffer is we can first find the hydrogen ion concentration, that equals Ka, concentration of the acid, divided by concentration of the conjugate base, and then we can calculate the pH equal negative log hydrogen ion concentration. Okay, and one more thing, let us take an example of acetic acid acetate ion buffer. So acetic acid is CH3COOH. That concentration will go in the numerator and its base is going to be, conjugate base is going to be, after removing one hydrogen, CH3COO minus, that is the acetate ion. And you can calculate from that H plus ion concentration pH of the buffer solution by using the formula negative log of hydrogen ion concentration. Either of this equation we can use. Okay, in this case, again, this is also going to be a two-step problem if only Ka is given. So that means we have to first find the pKa, negative log Ka. So then that's the first step. And the second step, substitute in the formula. If the pKa is directly given, it is easy to just substitute everything in the formula. Whereas in this case, first we are calculating the H plus ion concentration and then we are calculating the pH. Now let us practice some questions. Okay, we have a set of solutions here and we have to identify which solution is a buffer. So we know by definition a buffer is a combination of weak acid and its conjugate base, or a weak base and its conjugate acid. So that's what I'm going to look at it. So the combinations are, in the first one, HNO2 and HCl. So for the HNO2 we know, we can see that HNO2 is a weak acid, HCl is a strong acid. So by definition, this is not the buffer. And in the second case, HNO3 is a strong acid, NaNO3 is the salt, but the salt is not formed from a weak acid. It is from a strong acid. Okay, and also the salt is not formed from a weak base, right? So which is again not the definition for a buffer, so that is not the answer. HNO2, the next combination, HNO2 is a weak acid and NaCl is a salt. Again, the salt is not formed from a weak acid or a weak base, so that is not the buffer. HNO2 again in the next combination, so that is a weak acid, and NaNO2 is formed from a weak acid, HNO2. So that is our conjugate base or the salt of a conjugate base from a weak acid, right? So this is the buffer solution. So weak acid and its conjugate base, and another combination can be weak base and its conjugate acid to form a buffer. Okay, here is another question for the calculation of pH of a buffer that contains 1 molar acetic acid and 1 molar sodium acetate. So acetic acid is a weak acid and sodium acetate is the conjugate base or the salt of a conjugate base of acetic acid. So Ka of the acetic acid is also given. So we know the formula: concentration of hydrogen ion equal Ka concentration of the acid divided by concentration of the conjugate base. So let us substitute and find out the value of pH. So Ka is 1.8 times 10 to the power negative 5, and concentration of acid is 1 molar and the conjugate base is also 1 molar. So 1.8 times 10 to the power negative 5 is our H plus ion concentration, and we can find the pH negative log hydrogen ion concentration. So that equals negative log 1.8 times 10 to the power negative 5. So that equals 4.7. And that makes sense because that is a weak acid. So we can say a weak acid with a pH of 4.7. So that's an acidic buffer. Okay, next question. Calculate the pH of a buffer solution that contains 1 molar acetic acid and 2 molar sodium acetate. Ka of the acetic acid is given. So how can we solve this problem and how is it different from the previous one? So first we will start with the hydrogen ion concentration, which is Ka, concentration of the acid divided by concentration of base. So now we will substitute. Ka is 1.8 times 10 to the power negative 5. Concentration of the acid is 1 and concentration of the base is 2. So that equal, we will have 1.8, 1 over 2 is 0.5 times 10 to the power negative 5. So that equals 0.9 times 10 to the power negative 5. So by writing in scientific notation, we will get 9 times 10 to the power negative 6. And now we can substitute in pH formula negative log hydrogen ion concentration, that equals negative log 9 times 10 to the power negative 6. That equals 5.04 pH. Let's see this practice question. Calculate the pH of a buffer that results from mixing 0.03 molar benzoic acid and 0.15 molar sodium benzoate. For benzoic acid, Ka is given as 6.5 times 10 to the power negative 5. So we don't need to know the formula of benzoic acid or anything. We know it is not in the list of strong acids we learned. So it is a weak acid. And sodium acid benzoate. Benzoate is, you see, the benzoic acid. So benzoate is the salt formed by the conjugate base of that weak acid. So we can go ahead and substitute in our formula. Concentration of hydrogen ion equal Ka, concentration of the acid divided by concentration of base. And now let us substitute 6.5 times 10 to the power negative 5. Concentration of the acid is given as 0.03 and concentration of the base is given as 0.150. Okay, so in that case, we can substitute and we can find 6.5 times 10 to the power negative 5 times 0.2. So concentration of hydrogen ion equal 1.3 times 10 to the power negative 5. So now we can find the pH as usual, negative log hydrogen ion concentration that equal negative log 1.3 times 10 to the power negative 5 that equal 4.89. Okay, what is the pH of a solution consisting of 0.15 molar NH4Cl and 1.5 molar NH3? Kb is given. We can approach this question in two different ways. Either we can calculate pOH first and then subtract it from 14 to find the pH, or we can find the Ka first and then we can find the pH. So I'm going with the second method I mentioned. I will first find the Ka because I don't have to keep using different formula. So I'm going to keep that formula, hydrogen ion concentration equal Ka, concentration of acid divided by concentration of base. Okay, so now we can go ahead and substitute the values to find the Ka value. So Kb is given. How can I connect Ka and Kb is Ka times Kb equal Kw. So Ka I have to find. Kb is given as 1.8 times 10 to the power negative 5 and Kw is 10 to the power negative 14. So I'm going to find Ka by dividing on both sides by 1.8 times 10 to the power negative 5 that equals 0.55 times 10 to the power negative 9, or in scientific notation 5.5 times 10 to the power negative 10. And that's the first step. And the second step, I will find the hydrogen ion concentration. So that equal Ka, concentration of acid, divided by concentration of base as we shown in the beginning. And now Ka is 5.5 times 10 to the power negative 10. Concentration of acid is here, this is the acid, conjugate acid, this is the base. So concentration of the acid is 0.15 and base is 1.5. So that equal 5.5 times 10 to the power negative 11. When you simplify, you can see that one because this is the 0.15 divided by 1.5 will be 0.1 and 0.1 is 10 to the power negative 1. So 10 to the power negative 10 times 10 to the power negative 1 will be 10 to the power negative 11. After getting H plus concentration, we can find the pH. pH equal negative log hydrogen ion concentration. So negative log hydrogen ion concentration, we got it as 5.5 times 10 to the power negative 11. So that will be 10.23. And that makes sense because this is ammonia. Ammonia and ammonium chloride is a basic buffer. So for bases, pH will be above 7 and it is around 10.28. That makes sense, right? Now, the next question, we can say that calculate the pH of the buffer that results from mixing 50 milliliters of 0.2 molar acetic acid and 25 milliliters of 0.2 molar sodium acetate. So that's a weak acid and its conjugate base or the salt of a conjugate base, right? So we use the same formula and we can find, since the volumes are different, we just have to do one more step. So what is that means is, first I will find the number of moles separate. In this case, I can say millimoles. It's going to be the same. You can either calculate the moles or millimoles. So if you are converting on both cases, so it will remain same. So it doesn't matter millimoles or moles. So I'm going to calculate millimoles because it reduces the step and it doesn't make any difference in the calculation. Okay, how can we find? Because we have the molarity, we have what else? Volume, correct? And now we can find the number of moles by multiplying molarity and volume. Molarity is 0.2, volume is 50. That is for our acid. So I will just write number of moles of acid. So that will equal 10 millimoles. And for the base, I will calculate the same, that is the conjugate base, molarity times volume, which is 0.2 times 25, that will equal 2 times 25 is going to be 5 millimoles. So after getting the moles, I will recalculate the concentration, or we can directly use the millimoles. It's not going to make any difference. But let us go through the right method by converting into molarity. So that means now I have the number of moles of acid, and when we mix these two, we will have the total volume 50 plus 25, that equals 75 milliliters. So in 75 milliliter, when you mix these two, the number of moles will be different. The concentration will be different, I mean. So concentration of acid now will change us to, we have the moles and we have the volume. So moles divided by volume is 75, that equals 0.133, and concentration of base equal, I have 5 divided by 75, that equal 0.066 molar. So after getting that one, what I will do is, the next step is finding the concentration of hydrogen ion, which is Ka, concentration of acid divided by concentration of base. Why I did one more step here? Because we have different volumes, 50 milliliter and 25 milliliter. In previous cases, we were talking about the same volume. That's the reason. So Ka is given, since it is acetic acid, 1.8 times 10 to the power negative 5, and concentration of the new acid, the new concentration is 0.133 divided by 0.066, that equals 3.62 times 10 to the power negative 5. And now we can, as usual, find the pH, which is negative log hydrogen ion concentration, that will equal 4.4, and that makes sense because this is acetic acid, weak acid, pH is 4.4, so this is an acidic buffer. And now a little more advanced question. So calculate the pH of 0.5 liter of a buffer solution composed of 0.5 molar formic acid and 0.7 molar sodium formate before and after adding 10 milliliters of 1 molar HCl, and the Ka of the acid is given 1.8 times 10 to the power negative 4. So how is it different from the previous question is, we are going to calculate the pH after adding an invader. So we are adding an invader HCl. Okay, so let's go ahead and see how to approach this question. So before and after. So before, it's not going to make any difference. So we will use the same formula, that is concentration of hydrogen ion equal Ka, concentration of acid divided by concentration of base. Alright, so in that case, we can see Ka is 1.8 times 10 to the power negative 4. Concentration of the acid is given as 0.5. That is a formic acid. We don't have to know the formula here. And 0.7 is the sodium formate, which is the conjugate base. So that will equal 1.29 times 10 to the power negative 4. That's our hydrogen ion concentration. And then we can calculate pH, negative log hydrogen ion concentration. So that will be negative log 1.29 times 10 to the power negative 4. So now we can get this answer as 3.89. The pH is 3.89. So that's an acidic buffer. And now we have to use a different formula to calculate the pH after adding 10 milliliter of HCl invader. So the formula is going to be, to find the concentration of hydrogen ion, we can write concentration of hydrogen ion equal Ka, and now we are not going to use concentration, we are going to use number of moles. Number of moles of the original acid present in the buffer plus number of moles of acid added, that's the invader, and divided by number of moles of conjugate base originally in the buffer minus number of moles of acid added. So that makes sense, right? Because we are adding into the solution, we are adding, already there is acid and conjugate base. So we are adding acid means we have more acid in the solution, and some acid that we are adding will get the conjugate base will get neutralized by the acid. That's why we are subtracting from the base and we are adding to the acid. That's the reason for that. And now I will substitute the Ka value and the number of moles. So before I substitute, let us see how to calculate the number of moles of original acid. What am I having here is, for original acid is 0.5 molar. Okay, so 0.5 molar in 0.5 liter. So 0.5 times 0.5 will be 0.25 moles. And now the number of moles of conjugate base in the solution, buffer solution, will equal molarity times the volume. Volume is 0.5. Both are same volume, 0.5 liters. So that equals 0.35 moles. And now I want to calculate the number of moles of acid added. That is our invader. So when it is added, that means I have 10 milliliter. That means I will convert that one into liters, divide by 1000, so 0.01 liters times I have the concentration of 1 molar. So that will equal 0.01 moles. So I converted everything into moles. I just have to substitute now. So concentration of hydrogen ion equal Ka, the same formula, right? That is the number of moles of acid is 0.25 plus I have invader 0.01 divided by base is 0.35. I had to subtract 0.01. So Ka is 1.8 times 10 to the power negative 4, and we can simplify this one as 0.26 divided by 0.34. So we will have 3.86 as pH. After H plus, you can calculate the pH. So we will get that answer as 3.86. So we can see here that before adding the invader, the pH was 3.89, and after adding the invader, the pH we are getting 3.86. Not that much big difference, right? That's how it is always keeping the pH same. So that is why it is a buffer solution. So it's not changing the pH that much. Even after adding highly concentrated 1 molar hydrochloric acid, 10 ml, we are adding to that buffer solution, and it is not changing the pH that much.